so the I guess permutation argument of Plonk is something to make sure that the registers are wired. So when you build your circuit, you're just creating these gates. I don't know, visually this is how I'm saying it. You have like these rows, and you're just listing them, and in every row you have a register, I don't know, 0, register 1, register 2. So this is register 0, register 1, register 2, and maybe these are the two inputs, and this is the output, and you want to like wire the output to another row, and wire the output of that row to this one, for example, and make sure that the input of this row is the same as this row. So you sort of wire things around in your circuit, and to make sure that these are wired, and this is also called a copy constraint, which I guess is a good name as well. You use that permutation argument. So basically how it works is that there's this idea that if there's the grand product argument. Maybe I'm not going to talk about that just yet. But okay, the way it works is that they start with this accumulator thing. It's a series, and they say it starts at 1, and then every element of that series is calculated as the previous element times a fraction, and it's gonna refer to the grand product argument. And the fraction basically is like elements in your circuit, so the registers. So if you only had single elements, for example, your circuit was just one row of elements, and you just wanted to check that all the elements are So imagine you have two lists, okay, and you want to check that all the elements here are in the elements here. So one way you could do this is you take list 1, and it's also like a series, and you take list number 2, I'll call that L prime, and you do this thing. This is your fraction. And basically here, imagine you have 1, here you have 3, you have 5, here you have 1, here you have 3, here you have 5, right? Imagine these are short lists like this. What you will get is AC0 equal 1, AC1 equal 1 times 1 over 3, AC2 equals 1 over 3 times 5 over 1, and AC3 equals 1 over 3 times 5 over 1 times 3 over 5. That's the last of the list, right? And basically you will see that everything is supposed to cancel out, and here 1, right? And so basically the last, let's call it n, or final, whatever, is supposed to be 1, and that's the constraint. If indeed the last element here of this series is 1, then we know that everything here and everything here cancel one another, and that basically means that this list, or this, let's say this multiset, is equal to that multiset. Okay, so that's one way of doing it. Okay, I guess this is step 1, and basically one thing to say, okay, I'm gonna try to remember that on the spot, but this is actually not really accurate. So for example, we could have different lists. We could have a list that has 15, and here we could have 3 and 5, and here 1, and I think this is not going to work. So okay, let's see. AC0 equals 1, AC1 equals 15 over 3, and AC2 equals 15 over 3 times 1 over 5. Okay, and these things are going to cancel out, right? So AC3 is actually going to be equal to 1. So I found one example where this doesn't work, and my argument there doesn't work. So the way you fix this is by introducing a gamma, so a challenge from the verifier, and making the protocol by making this protocol interactive. So basically, you're gonna modify this this equation, and you're gonna put a gamma here, and basically now this wouldn't work because this would be gamma times 15, gamma minus 1, and here gamma minus 15, gamma minus 1, gamma minus 3, gamma minus, oh, what am I doing? 3, 3, 1, 5. Okay, and I guess you can open up this thing and see that it's gamma square minus 15, plus 15 minus 15 gamma minus 16 gamma, right? And here it's gamma square minus 8 gamma plus 15. So obviously you can tell this might cancel, but okay, these are not going to cancel because they're completely different polynomials. Okay, so that fixed the problem, and if you really want to see why it fixes the problem, basically you have to use the Schwartz, and I can never spell it, so let's try Schwartz Zippel. Hopefully this is right. The Schwartz Zippel lemma, and basically it tells you that if you have two polynomials with roots that take roots in these lists, then maybe let's write it like this. These polynomials is going to be equal to this polynomial. It's going to be equal to this polynomial in most points. And if these polynomials differ, so if the coefficients here differ, then these polynomials are going to be different in most points. So you can just try it at a point gamma, and if they differ at that point gamma, so if you cannot do that division, right, that fraction or that grand product argument at some point gamma, then you know that they are not the same polynomials, meaning that their coefficients are different, meaning that basically there are different multisets. Okay, so the second step was to show how to do a multiset argument. So we introduced this gamma. Okay, third step is going to actually check that there are permutations. So a multiset argument checks that these are the same multisets, and so it's the same as checking that this thing here is a permutation of this thing. But we want to do more. We want to check that it's our permutation. Like you want to check that this permutation here on the left corner is fixed, and we're really checking that permutation, not any permutation. And so sometimes you actually don't care about that, but here in that copy constraint, these are fixed. So let's call that third step, the permutation step. Okay, so notice here I only dealt with two lists, and I didn't, these lists have indexes, right? This one is like maybe the first element or the second element, third element. So I really want that to be part of I want the first element to match with maybe the second element right here, right? And I don't want it to match with the third element. So maybe that's my wiring. This thing is wired to the second element. So basically what I do is that here I also introduce the index, and I cannot just write like, I, li, this is a tuple, this doesn't make any sense in math. So basically what I do is that I introduce another challenge, and the way I do it is that basically, okay, my tuple is this thing, or if you want to be more, if you want to be more general, my tuple was A and B, so I represent it at A plus some challenge B. So that's one very handy way of representing things, representing tuple in an argument like that, and this is a verifier challenge as well. So okay, let's write the equation I plus, oh, it's not going to be I here, actually. We're going to do the permutation of I plus beta L Li prime. Okay, and this sigma I is going to, so if I pass 1 here, it's going to give me 2, because that's the, I want 1 to be linked to 2 here, so 1 linked to 2. So that's going to be a function. Or for now we can also say that it's just a series as well, because we're going to transform everything as polynomial down the line, but now we're using series. So okay, does that look correct? Okay, it doesn't look correct because it's the other way around, right? It's 2 is sent to 1. I mean, yeah, okay, that's correct, because this is gonna be 2 in this list, in that second list that we're sending here to 1, and maybe the 1 here in the second list will send it to 3, right? So s of 3 is gonna be equal to 1, and s of 1 equal to 3. What am I saying? Sigma of 3 is going to be equal to 2, right? I think that's right. You can tell me if it's wrong. Okay, so now we have a permutation, and to do that permutation, we just introduce that that beta here to transform. Well, we introduced an index, which is just I guess. And or it could be, another series if we wanted, and we introduced a sigma and this challenge. Cool. Okay, so now how do we go back to our registers, our 3 registers, or columns, or wires, or in Plonk this would be, I guess, A, B, and C. Here, maybe let's try and use that. A, B, and C. First step, that's the first step, is okay, Plonk, the linking to Plonk. We're okay. Let's make some room here. Maybe this is the slowest way of deleting. Okay, let's delete these things. I'm gonna need some room. Okay, so now we're not going to use Li and L prime I. We're actually going to use our witness. So here is going to be AI, here is going to be AI as well, and we have 3 of them. So basically we'll write the next one I plus beta. Oh wait, so we'll write them like this, because these are several elements now. And here we could do a minus or plus. I don't think it really matters. Same with here. I guess it doesn't really matter. So maybe let's just write plus everywhere. And let's write bi, and gamma plus I plus beta ci. So now we really have a grand product argument, like a multiplication with all of these terms. They're kind of on the same they're kind of in the same list, and they're going to mess with one another. So actually this doesn't work. And the trick here is to actually, and I'm gonna explain it very quickly, but is to add another element, and to make it look like they're on different to make it look like they're not on the same same index, but they're on different index. Really separate the index of every list. So this one is from, I don't know, 1 to n, but this one will be from we want to do some. So yeah, we kind of want to take this list from 1 to n, but this list is from n to 2n, and this list is from 2n to 3n. Like that, these indexes don't mess with one another. Otherwise, we're like looking at the same list. There's going to be any collisions, So the way we fix that, I guess, is to introduce like a k, and you can think of k as being like n here. Well, actually, that wouldn't work. Okay, we just introduce a k here, k1, here k2. Actually, let me rewrite this. Plus k1 times I, and here plus k2 times I. Okay, and these are going to be cosets. So I'm not going to explain that here. Maybe I should. Maybe I should. Yeah. Maybe I'll do another video. And so here you need exactly the same down below. Gamma plus k sigma 2 I. All right, let's call it sigma prime I plus beta bi. And gamma plus k1 k2 sigma prime plus beta ci. Okay, so also remember that this sigma I equals I if there is no permutation, right? So that for example 3 is wired to itself, A3, then you'll have the denominator will look like 3 plus beta A3, and they will cancel one another, okay, if there is no wiring. Well, okay, so this is pretty much the final equation for the permutation. It looks like that. It's a bit messy, but I guess you can just say it's like the sum of gamma plus like ki or something like that, with like the first k being just 1 times I plus beta value I don't know, you could simplify it, but it looks like that. If you look at the paper, it'll look like a mess like this. Okay, so there's one last step, 5, and the last step is polynomials. How do you translate that into polynomials so that you can actually put that into your proof system? And the way you do this is that you polynomialize your series. So AI, BI, CI, we already have the AX, BX, CX, we already have these. This sigma and sigma prime and sigma prime prime are basically going to be polynomial. So you take, sigma of 1 will be equal to 2 and stuff like that. So this is pretty easy. Gamma and beta are just challenges, so they're going to be values. And do we need anything else? Oh, and I guess the k's, k1, k2 are also going to be values, so we're not going to care too much about that. Oh, and there's I also, and I is basically going to be x, because we go through every point. We're gonna go through every point, so I becomes x. So that's gonna be the transformation. So let's try to write it down. Basically, hack is going to be a polynomial, and we're gonna send that as part of the proof. And we're gonna say that we cannot do division actually. So we're gonna move that denominator part here. So we're gonna say hack. Oh, so now we have hack I plus 1 equals hack I times this fraction, or we're gonna move that j and we're gonna put it here. Oh. And we're gonna say constraint this. And here we're actually gonna look at I plus 1, and we're gonna say these are polynomials. We're gonna say hack of x. Oops, hack of x, f of x, j of x. And here for I plus 1, we're gonna say hack. That's where it's hard. We're gonna say x plus 1, I guess. In Plonk, actually, they don't use 1, 2, 3 as points. They use like j square, j cube, etc. So here we're just gonna say x times j. So if x is j square, then x times j will be g cube. So that's how they write it. Okay, and so they're gonna say basically the constraint is gonna be that not that they're equal, but that the subtraction equals 0. That's how you constrain things. And you're gonna also say that hack of x equals 1. Wait, that's the 1. The second constraint is gonna be that hack of x equals 1 for the initial value. And so the way you do this is that you say this is true for x equal j. That's in Plonk, that's the first value. And third, hack of x minus 1 equals 0 also for x equals the last value, for x equals g to the n or something like that. Okay, so I guess that's the permutation argument. And the way this works basically is that you take the Lagrange basis. So this is another thing I should explain, I guess. L0 of x equals 0, and here we have Ln of x equals 0. These are Lagrange basis. And yeah, I guess I'm not gonna explain it here, but basically you can think of Li of Gi equal 1, sorry, for for 1 for I equals j, and 0 otherwise. That's pretty much Lagrange basis, and that's very easy to compute. So in our protocol, we're actually going to send hack to the verifier, like commitment to hack, and then the verifier will send. Oh, and actually before that, we'll send commitments of other stuff, all the stuff that are involved. The verifier will send us beta and gamma, so we can construct hack. Then we send the commitment to hack. Then they send us, at some point they'll send us 2 evaluation points, x1. Oh, sorry, they send us x1, and then we have to send hack x1 and hack x1 times j. And in Plonk they call that zeta, by the way. and then they send us this, and then we can actually check if this is true. Okay. Okay, so what am I missing? Okay, I guess this is when zero knowledge rows come into place, and when you're sending this ACK, it's a secret polynomial because it involves these witness values, the secret values. And so when you evaluate ACK at 2 points, at these 2 evaluation points, and by the way, again, you need this evaluation here because of here. You cannot check your equation without it. When you evaluate the polynomial at 2 points, you might be leaking some information. Very little information, but we want to add zero knowledge. So basically the way we do this is that the ACK emitter is like, ACK 0 equal 1, ACK L plus 1 equal this, and then the final value is 1. And then we say ACK n plus 1 equal some random value, and ACK n plus 2 equals some other random value. So basically we add some rows. So when we have these constraints here, we just need to make sure that these constraints don't apply on these last rows. So these 2 constraints are fine because they only apply on the rows that we're talking about, but this constraint is not fine because it applies on all the rows. And actually it should really not apply on the last row here. So we already made a mistake here. We should have written this times basically some polynomial t, where t of x equals, well, let's write it here like that I can reuse, where t of x equals 1 for all x except x equal n. That's the last constraint, so we don't want it to apply there. And then we don't want to apply it on the new constraints here, or the new values here, which are randomized. So we say except x equal n, n plus 1, and n plus 2, basically. And that's the way we avoid the zk rows, or not just the zk rows, but the zk rows and the final row also.